Page 101.
10.
Page 101, number 10.
Yes, that's what I wanted to ask.
Okay, number 10. Show that the set blah forms a group under composition of functions. This one?
Yeah, I understand this.
Well, I'm surprised that you understand just most of it, not all of it.
I think it was just.
Well, okay, well, let's look. So, what is going on here? We have our set S is all real numbers, right? Functions which we're considering, how they're denoted? FAB?
Yeah, M.
Huh?
M.
MB? Ah, that's because that's how you're writing it in. Okay. M is a slope. It is FXB, MX plus B, right? It's called slope-intercept form, if I remember.
It says that m can't be 0.
Now, M, of course, cannot be 0, because if M is 0, it's not a bijection. We're interested only in bijections. Now, this is certainly a bijection. How do I know that? Well, the graph is straight line, or if I write that m of x plus b is equal to y, I can solve it. Right? Then x is y minus b divided by m, which I can safely do because you told me that m is not 0. So it's 1 to 1, and it's on to right, because for any y I can find x. So this is a bijection. So this is element of sim of all real numbers. Of course, I'm not going to discuss precise definition of sim. Okay, you can think that it's all bijections.
Hey, what?
That it's all bijections are. Okay, so what should you check? Closure. Subset closure. Okay. So in order to do it, you have to take composition of two functions like this, right? And check whether it's a function like this. And this is exercise from 180 or whatever it's called, I don't know. M1x plus, what is it here? M2, I'm sorry. M2x plus B2, right? And what I'm doing with input should be multiplied by M1, whatever it is. Right? And then B1 should be added. Okay? And so you will see M1, M2x plus M1, B2 plus B1. So it is F M1, M2, M1, B2 plus B1. Again, function of the same kind. Okay. Now, if you want, you can proceed. You can understand that identity is there, right? Because actually, F10 is identity. Right? And then you can figure out what is inverse of it. But genetically, it's clear that if you have a function with graph which is given by slanted line, slanted because n is not 0, and of course not infinity, right? Then inverse of it also will be function with graph which is slanted line. Actually, you saw this group before, but not over real numbers, over Z5. Do you remember you had a question about a group which was given by matrices M, B, 0, 1. Do you remember it? Okay, let me multiply two matrices like this. And 1 and 2, right? That's correct. Okay, now I have M1, B2 plus B1, 0, 1. How about that? M1 and 2, M1 and 2. So actually it's the same rule. Actually it's the same rule. So what was the problem? What was confusing?
What's affine?
I think I'm still confused at what the inverse is.
Okay, fine. What was your question?
What are affine functions?
It's just definition. It's just definition. Functions like this are called affine.
What does it mean?
Okay, here is okay. You remember what are linear functions? Linear transformations? Now, when you were learning things like this, you were calling these linear functions, which is not quite correct, because they are not linear transformations. Only when b is 0, it's linear transformation. So, actually, transformation of a vector space, which works like linear transformation, plus shift by a vector, such a thing is called a affine function. That's just definition. Okay. Inverse. Inverse. Well, here is inverse. Okay, so f m b inverse is f 1 over m minus b over m. And I think when we were dealing with matrices, it was not a problem. The reason is that composition of fmb and fmb inverse is f10. That's it. So I'm sure that if not for all this wording, you know how to find inverse function in this simple case. Okay, more questions. I'm stuck with you for 1 more hour. You know, you have to ask me questions.
For that
Yes.
group, it can't be abelian for all of that. It can't be abelian for all of its.
Well, it can be, but it isn't.
But it's not, right?
Yeah, you can check it. And what's the reason? That, you know, you don't know, you have to check it. The point here is that if you switch the order, result will be m2 m1, m2 b1 plus b2. Okay? So slopes are the same. But this is not necessarily the same. Yeah, and it's the same. And you did this exercise on level of these matrices. I don't know, it was not asked whether it's abelian or not, but.
But I just had a math lesson 5,000, and we like it was like that question. This question was on it.
Okay.
I was like, no.
So, okay. So, you know, when you're given particular group and you are asked whether it's abelian or not,
He said
you just have to check it. And again, it is non-abelian if you produce 2 elements which don't commute. If you want to show that it's abelian, you have to check the thing there. Any questions?
Yeah, but.
Go ahead. Go ahead. Don't be shy. You know.
On 102.
Next page. Yes.
20. Like, I know that it's.
Number 20.
Yeah.
Okay. S is non-empty finite set with a binary operation that satisfies the associativity law. Show that S is a group if blah implies blah and blah implies blah. What can you say if S is infinite? Well, we'll see what we can say if S is infinite. Let's start with finite S. Okay, so what do we have? We have a set S, which is finite, right? We have some iteration on S, which is associative, which is satisfactory, so it won't be associative, we cannot talk about it. With 2 properties, right? A star B is A star C implies B C. B star A, C star A implies B, right? Anything else? Okay. Yeah. So it's like in group constellation. Claim is that then S is a group, right?
When it says binary operation, is that closed? Does that mean it's closed?
Yes.
Okay.
Yeah. Oh, yeah. Okay. Because read the wording. What is? There is a binary operation, and
Yeah.
what? How it is written?
Finite set with a binary operation star that satisfies.
Okay. So set has a binary operation. It means that when inputs, right, or binary operation on a set, but yeah, it certainly means that this thing is in the set, not elsewhere. Okay, so what we are missing? We have a set S with associative operation. Wonderful. So what we're missing to claim that it's a group?
And it's closed, right?
It's-
Okay, so we just need to do the identity.
It defined on a set. So
Inverse
what I'm trying to push you is to remind me the axioms of a group.
identity.
Aha, okay. So we have whatever to identity with property EA is equal to AE is equal to A. Okay. So in our situation we have the beginning, but we don't know whether we have identity. We don't have identity. Okay. So I have to find identity. Well, one idea is that because A multiplies A, so I'll consider mapping of A from S to S. You understand which one, right? It takes element B, let me, I don't know, denote it, FA. FA of B is A not multiply. A mumba jumba B, right? A star B. Which, suppose I have identity, then certainly FA, F sub A of identity must be equal to A, right? Of course I don't know if I have identity or not. Well, it is a finite set, and this property tells me that it is one-to-one. That function fa is one-to-one. Agreed? Since this is a finite set, what can I conclude? This function is also, aha. So image, so if I write fa applied to S, it certainly contains A. Agreed? Now I already see what will go wrong if I don't assume that S is finite. If S is infinite, I cannot make this conclusion. Right? Because one-to-one on infinite set doesn't denote. Okay, so what it means? That there is some element such that when I move a jumbo it with A, but with A only, that's why I'm writing E with A. Result is A. So that's good. Now, if indeed I have identity, then this element must be identity, because it's impossible, right? You understand? But of course, now I have a challenge. So, for example, Y is equal to A. Why? I don't know. I have to look at it, right? And more importantly, maybe that this EI will work for other elements. So that's what I have to somehow figure out. I have the only possible candidate for identity, but now I have to check that it works like identity. Because I take other elements instead of A, I'll get other. So apparently, my only hope is that this is associative operation. This is, and we have these properties. So let's try. So that's what I have. That's what I don't have. So, how about something like this? Take A with EA and apply it to B, right? And using that operation as associative, you can write that this is A applied to B, right? No matter, since here I can put brackets the way I like, so this would be A, okay, right? Now I'll put brackets like this, okay? So far so good. And then I say, by property 1, EA start with B is equal to B. By this cancellation property. It's kind of cute, yeah? EA worked as identity for A on the right, and from this we deduce that it worked like identity on the left for all B. For this matter, B can be A, you understand? It's any element. After that, you understand that we're done. Yeah? Because now this works as left identity. I can write now E left star with B is equal to B. Okay. So it works as left identity for A as well. That was my concern. Right? And now what I need to show that it also works like right identity. But now you understand how to do it. Multiply it by C here. Okay. And then by putting brackets like this, you can cancel it, and so C start with the C and so on. And once again in the process we understood why it was essential for us that set is finite. Only because it was finite, by pigeonhole principle, we concluded that it's only. If it's infinite, we don't have this conclusion, generally speaking. Now, of course, it doesn't mean that we disprove that the same is true for infinite set. We just show that this proof won't work. Okay? Now, in order to have completely satisfactory situation, and I'm not going to do it, is to think about infinite set and try to build an example operation like this, so that we don't have these conclusions. It shouldn't be too hard, but let me ask other questions. Okay? I'm sure you have a bunch of questions. So, sure.
Listening.
You're okay? Good. I'm happy to hear.
Can you do this? It's like if you let G be a finite group and then H is a normal subgroup of G, that you have to prove that the order of an element of G times that subgroup and the factor group of GH divides the order of G.
Okay, we discussed it in greater generality, and then I explained how it's connected in the following situation. Suppose I have a homomorphism from group A to group B. Homomorphism. Then order of phi of A divides order of A. It's true for any homomorphism. So let me remind you how we proved it. If order of A is n, then A in power n is identity, then phi of A in power n is phi of identity is identity, but this on the other hand, since it's a homomorphism, phi of A in power n, so phi of A in power n is also identity. Which doesn't mean that this n is order of phi of A, but it means that order of phi of A divides n. So in this situation which you described, it's just special case. Because if you have G, you have a normal subgroup, then you have a homomorphism from G to G factor H, right? And that's the application of this more general statement. That's exactly what's happening, because phi of G is class of G, right?
Yeah.
So order of G is divisible by order of its integer. That's it. So it's just special case.
Was that a proposition or theorem or something?
Yeah, it's,
Good save.
Yeah.
Parsons and stuff.
Huh? No, next question.